Hello everyone, so today we're going to talk about Einstein's theory of special relativity. So in this screencast, I'm going to go over initial reference frames, Einstein's postulates, connection to astronomy, so the connection between relativity and astronomy, time dilation, and length contraction. So first let's talk about initial reference frame. All motion can be described relative to resting objects or systems/frames. An inertial reference frame is basically a frame that's motionless or has a constant velocity, and objects are going to move relative to the inertial frame. So in an inertial reference frame, no acceleration happens. There's either that frame is either resting or it's at constant velocity. So in this example, we see that we have two inertial reference frames. And here we have a person who is standing at rest, and here we have a car that's moving at 90 kilometers per hour. So for this person, if this person sees a car on a road that's moving at 100 kilometers per hour, the person is going to observe 100 kilometers per hour. However, if the same person was inside a car that was traveling 90 kilometers per hour, then they're going to observe the same car travel at 10 kilometers per hour. However, light does not behave in this way. With light, if you're a person at rest and you're seeing a beam of light shoot past you, you're going to measure the speed at 3 times 10 to the 6 meters per second. But similarly, if you were the same person in a rocket and this rocket is traveling at speeds approaching the velocity of light, so in this case it's 299 million meters per second, well, you're going to observe the speed of light, which is basically this beam of light shooting past you at the same speed of 3 times 10 to the 6 meters per second. So basically, at really high speeds, strange things happen. Before we talk about Einstein's postulates, it's important to think about kind of the context behind at this time, and also what led to Einstein kind of crafting these postulates. So during this time, scientists thought that light was only a wave, and so all electromagnetic waves needed some sort of medium to travel through. Ocean waves needed water to travel through, and then sound waves need air to travel through. So scientists proposed that a vacuum wasn't really empty and that light traveled through the existence of an ether in a vacuum. Also, if light is a wave, then it should be able to travel in different direction, like how ocean waves travel in different direction. So to highlight this, let's look at this example here. Here's a sailboat, and if it's traveling with the current, it's going to go fast, and if it's traveling against the current, it's going to go slow. So using this kind of ideology, Einstein devised an experiment where there is some light source which emits a light that hits this mirror, and then it's going to go to this mirror. Some of the light is going to go to this mirror, and some of this light is going to go to this mirror over here. Just kind of thinking about the with current and with against current, Einstein hypothesized that the wave here should be faster than the green wave. However, the detector picked up that these waves were the same speed of 3 times 10 to the 6 meters per second. So now let's go ahead and discuss Einstein's postulates. So the first postulate states that the law of physics is the same for every inertial frames, and this we already know from the past few slides. The second postulate, which is very important, states that the speed of light in a vacuum is the same for every reference frame. This is because the speed of light is the universal speed limit, and this is verified through a lot of mathematical proofs. So for a person in the ground at rest and in a spaceship moving at a constant velocity, to measure the same speed of light, they must be observing time in different ways. And this is where the idea of space-time, time dilation, and length contraction all kind of stem from. So space-time is the idea that time flows at different rates for different observers. Basically, time is relative, and this is really a huge kind of mind-boggling part of special relativity. Space-time also affects biological clocks, so going at really fast speeds also affects biological clocks, and we see this through the twin paradox. Basically, if there are two twins, and then one of the twins went on a rocket at speed approaching the velocity of light, and then they went for some time and they came back, then this twin on the rocket is going to observe time differently than this person who is staying there on Earth. And so during that trip, time was much slower for this person on the rocket than the twin who was staying on Earth, and therefore this person on the rocket is going to be much younger than this person on the on Earth. And we can actually calculate how these two different people observe time differently. And we'll see that in the next slides. Before we move on, let's go ahead and talk about the connection between special relativity to astronomy. While special relativity goes very much against our intuition of how we experience time, there is a lot of verifications for it. So for example, this is probably one of the most common forms of verifications to special relativity and relativity in general. Mercury's orbit varies by 1 million from what we predicted by Newton's laws. And this is because, space-time is warped around the sun. Because the sun is such a massive object and because it has such strong gravitational fields, it's able to bend, space and time slightly, which accounts for this difference in Mercury's orbit times. Also, let's go ahead and talk about an experiment that was done that really kind of showed that light is able to bend in the presence of gravitational fields, and this just verified the idea of relativity in terms of light. So we know that gravity is a form of acceleration, and this also extends to electromagnetic waves like light. Scientists knew that at this time, in the presence of gravitational fields, light should bend. And so there just has to be some sort of verification for it. The best way to verify this would be during a total solar eclipse, because it would be possible to see the star near sun without the sunlight, since there was no sunlight. So light rays in the presence of the corona deviate from the star by 1.74 arc seconds because of its gravitational field. There were 2 expeditions led by Davidson and Eddington, and they went to parallel points at the equator to photograph the star during the solar eclipse. And the reason why they went to the equator was because, remember that solar eclipses have a certain umbra and penumbra, so they can't be seen all around the Earth. And so the equator fell underneath the penumbra of the solar eclipse. When they photographed the star's location and they compared it to the real location of the star, which was calculated through telescopes, they found evidence that the stars were located differently. So the apparent location of the star, which they observed, was different than the true location of the star. And that confirmed relativity and special relativity. Another connection to astronomy, which was done more recently and is pretty similar to the Mercury example, is that in the center of the Milky Way galaxy, there's three stars forming a cluster orbiting the supermassive black hole. So right here is a supermassive black hole, and these are the 3 stars that are orbiting them and their orbit. So one of the stars, S2, showed slight deviation in its orbits than predicted due to relativistic effects, and that's because massive objects like black holes bend space and time around them, and this causes other objects to deviate from their usual orbit. That's just because of gravity. So not only would you have to consider gravity, but you would also have to consider the relativistic effects. Also, it's important to note that stars move really fast, about 1 to 2% of the speed of light, which also might have impacted the relativistic effects observed. Now let's talk about time dilation. And to really understand time dilation, it's important to look at it through a thought experiment. So suppose you have 2 observers, a rocket and a person standing on Earth. So first let's look at what's happening with the person who's on the rocket. There's a light beam that's in the rocket, which is here in yellow, and it's going up and down. It's emitted by this source here, and it's traveling up and down, up and down. And so the total distance that it goes is 2d, so the length from the ceiling to the light particle is going to be d, so it goes up and down, that's going to be 2d. We know that time is equal to distance over speed. This is derived from the equation speed is equal to distance over time. You just rearrange a couple of terms. And so the time that this person sees is going to be 2d over c, because that's the speed of light, right? And so the time that this person on the rocket experiences, delta t naught, equals 2d over c. Now let's look at this in perspective from a person on Earth. So for an observer on Earth, we not only have to account the upwards and downwards motion of the particle, but we also have to account for the movement of the rocket and the path that it makes, and the path that the light beam makes as the rocket moves. And so what this observer is going to see is kind of the particle going up, and then the rocket's moving right, and the particle is moving down, and as the rocket continues to move right. So the distance, that going again from the same formula, time equals distance over speed, this person, this observer on Earth, experiences the distance, which is the kind of the length of the triangles here, not d. So after doing the Pythagorean formula, we get that the distance 2s, which is the distance it takes for a particle to go up and down, is going to be 2 times square root of d squared plus L squared. And then from there, the speed of light is still going to be c. So in this case, delta t, which is the time for observer on Earth, is going to be 2 times square root of d squared plus L squared over c. Notice how this delta time, which is the time that the observer is kind of experiencing, is longer than the time that the rocket experiences, observer on a rocket, which is 2d over c. So this just shows that time is moving slower for the rocket person than for the person on Earth, and it also confirms the twin paradox. Here's an animation that kind of shows the same concept, easier to visualize. So for the person who is in the rocket, they're going to see the light beam moving this way, and then an observer on Earth is going to see the light beam going up and down towards the right. Now let's look at some, and connect the idea of time dilation to reference frames. So proper time is the time intervals observed in a reference frame, which is not moving relative to the event being observed. So this is really your inertial reference frame you could think of. In this case, proper time is going to be the rocket. Even though it's moving and the observer is at rest, notice how that's where the light comes from, and it's moving at a constant velocity. So we can definitely say it's the inertial reference frame. Dilated time is the time interval where the reference frame is moving relative to the observed event. In this case, the observed event is going to be the light beam, and so the observer is kind of moving, with quotation marks, relative to this light beam. The observer on Earth is not experiencing directly this light beam as it is, and so they're going to experience the dilated time. So the basic idea is that there's the observer and the person on the rocket are experiencing time in different ways. So really great equation that is associated with time dilation is going to be delta t, which is the proper time interval. In this case, it's the spaceship, equals delta t naught, which is the dilated time interval with the person, over 1 minus square root of 1 minus velocity squared over speed of light squared. So you can do some pretty cool calculations with this. In this example, we have a rocket that's taking 1 year to move, and its velocity is at 0.8 times c. If we plug these into the equation, we can find out the time that is experienced by the person, which is going to be 1.67 years. So 1 year over square root of 1 minus 0.64 c squared is going to be 1.67 years. So notice how this person is observing a much longer distance than this rocket here. Now let's discuss some practical applications, as well as another kind of verification for special relativity. So since satellites move so fast, their clocks are programmed to have the same time as Earth, since the satellite experiences time slower. And this is very similar, the math kind of used is very similar to the time dilation equation, with obviously some more steps in them. Also, notice that as velocity becomes way less than the speed of light, then you're going to see that this is going to be like, let's say this is 0, right? As this approaches 0, you're going to get the square root of 1, which is 1. And so plugging that back into the equation, you will get delta t equals delta t naught, which shows that the time, both the relativistic time, so the dilated time, and the proper time are equal to each other at low speeds. That's why you don't really experience the special relativity when you're here on Earth at slow speeds. A really great example of observing special relativity are muons. So muons are subatomic particles with a known decay rate, and they can get really fast. It's been experimentally confirmed that when muons travel at speeds near light, their decay rate changes, and they can travel very far distances than they can normally do in the same amount of time. Or in the yeah, so the stationary observers also noticed that muons' half-life seems to increase. So not only is it there are they changing distance, but they're also changing their time. And this really proves the idea of time dilation and length contraction, which we will see later on. So here in this graphic really illustrates this way better. First, you have someone from the muon. So the muon itself, it's going to its half-life at really high speeds. It's going to experience this half-life here, this time, and it's going to be created, and then it's going to decay, and it's going to travel this much distance. So if you were a muon. But if you were a person from Earth who is observing the muon, then you would notice that its lifetime is actually way larger than this lifetime that the muon experiences. And the distance that it travels is going to be way greater. So in this case, both the mu and the muon experience time differently because of how fast the muon goes. To wrap things up, we're just going to go ahead and talk about length contraction. Similar to how time is relative, length is also relative, and it's also connected to the idea of time dilation. At very fast speeds, objects and distances appear shorter, and at slow speeds, objects and distances appear longer. So at fast speeds, time slows down and distance is shortened, so particles going near the speed of light can travel in less times. So to again kind of illustrate this point of length contraction, let's think about two scenarios. So in one scenario, we have the Earth as the inertial frame, and in another scenario, we have the rocket, not the planet, the rocket as an inertial frame. So in Earth as an inertial frame, the journey seems a lot longer, and the ship seems a lot shorter, especially as it goes away from you. But if you were on the rocket and you were the inertial frame, and the rocket is moving at a constant velocity, then the ship is going to seem longer, and you're going to experience a shorter journey. So the length here is going to be contracted. And we can kind of show this relationship through this formula. And so you'll notice that as the velocity is equivalent to the speed of light, then this is going to be 1 minus 1, which is square root of 0, which is basically does not exist. It's infinity. And that's why speed of light is pretty much the universal speed limit. Also, notice how if the velocity is approaching 0, it's going really slow, then this L is going to equal L naught, and so proper length is going to equal contracted length at really slow speeds, and that kind of reiterates the previously discussed concept where we don't really observe special relativity at our normal, at like the normal things we do on Earth. And that's it for special relativity. This was definitely a boggling concept to understand, and there are a lot of things that you can go really deep into, but this video just kind of serves to present the most important findings or more kind of general ideas of special relativity, and you can go really deep with this concept.